The universe is mostly made of something we cannot see. Over 95% of all energy and matter is completely missing from our cosmic inventory, a ghost in the machine of reality. This is the greatest unsolved puzzle in all of physics. We will journey through 30 mind-bending theories, from the strange push of dark energy to the possibility that our entire cosmos is a holographic projection. By the end, you will have a complete map of the boldest ideas trying to explain the fundamental nature of everything. We will ask if gravity itself is an illusion and whether empty space holds the ultimate secret. What is your gut feeling about what makes up the cosmos? Our journey begins with the leading theory, a concept so profound it reshaped our entire understanding of cosmic fate. This is the story of dark energy. Picture the universe not as a static stage, but as a living, breathing entity that is actively stretching. For most of the 20th century, scientists believed this expansion was slowing down, that the collective gravity of all the galaxies was gradually putting the brakes on the Big Bang. Then, in the late 1990s, two independent teams of astronomers made a shocking discovery. They were observing distant stellar explosions, known as Type I, a supernova, which act as cosmic mile markers. These supernovae have a known intrinsic brightness, so by measuring how dim they appear from Earth, we can calculate their distance. The teams expected to find that the most ancient, faraway explosions were brighter than expected, a sign that the universe's expansion was decelerating in the past. Instead, they found the opposite. The supernovae were fainter. This meant these stellar beacons were much farther away than anyone had predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was pushing galaxies apart from one another at an ever-increasing rate. This force was named dark energy. The evidence did not stop there. Independent measurements of the cosmic microwave background, the faint afterglow of the Big Bang, also pointed to the existence of this strange energy. The precise patterns in this ancient light revealed that the geometry of the universe is flat, which only makes sense if a vast, unseen energy component exists, outweighing all ordinary matter and dark matter combined. To explain this, physicists revived an old idea from Albert Einstein himself. Decades earlier, Einstein had inserted a fudge factor into his equations of general relativity, called the cosmological constant. He initially used it to force the universe to be static and unchanging, a notion he later called his greatest blunder when the expansion of the universe was discovered. But now, it seemed Einstein was right for the wrong reason. The cosmological constant could represent a constant energy density inherent to the fabric of empty space itself. This vacuum energy would have a negative pressure, generating a gravitational repulsion that drives the cosmos apart. Think of the universe as a loaf of raisin bread baking in an oven. The raisins are galaxies. If the dough is rising at an accelerating rate, the raisins will fly away from each other faster and faster. Dark energy is the yeast causing that runaway expansion. So, the most accepted answer to the missing energy problem is that the cosmos is filled with this smooth, uniform dark energy, accounting for about 68% of everything. Yet, calling it the leading theory does not mean the mystery is solved. The calculated value of this vacuum energy is a staggering 120 orders of magnitude off from what quantum field theory predicts. This is perhaps the worst theoretical prediction in the entire history of science. So, while dark energy is our best clue, it is also a profound reminder of how much we have left to understand. Yet this constant energy is not the only possible culprit. What if the force driving cosmic acceleration is not a fixed feature of space, but something that breathes and changes? This leads us to our second theory, a concept called quintessence. Imagine dark energy not as a static background, but as a dynamic, cosmic field that can evolve, weaken, or strengthen across the vast stretches of cosmic history. Quintessence is a hypothetical form of energy that functions as a fifth fundamental force, a distant cousin to the fields that govern particles and forces we know. Unlike the rigid cosmological constant, quintessence is a scalar field, meaning its value can shift over time and space. Think of it like the weather in our cosmic atmosphere. The cosmological constant is a perpetual, unchanging high-pressure system, while quintessence is a shifting front, with its own storms and calms that could alter the ultimate fate of the universe. The key difference lies in their equation of state, a number that describes the relationship between the pressure and density of this energy. For the cosmological constant, this number is fixed at exactly -1. For quintessence, it can be different, potentially greater than -1. In practical terms, this means the repulsive push of quintessence could have been weaker in the past and might become stronger or even fade away in the distant future. This opens up dramatic possibilities. If quintessence is real, the universe's accelerated expansion might not be a permanent sentence. It could one day slow, stop, or even reverse, leading to a cataclysmic big crunch, a scenario completely off the table with a simple cosmological constant. How could we ever tell these two apart? The answer lies in peering deeper into the cosmos. Astronomers are designing next-generation telescopes to measure the expansion history of the universe with unprecedented precision. By observing billions of galaxies and mapping the large-scale structure of the cosmos, they will look for tiny variations in the rate of expansion over billions of years. If they find that the strength of dark energy has changed over time, it would be a monumental discovery, pointing directly to a dynamic field like quintessence and shattering the notion of a simple, constant vacuum energy. This transforms the mystery from a single question into an active investigation. Is the cosmos being pushed apart by the unwavering character of empty space? Or is it being shaped by a fluid, evolving force that holds its own secret history? But what if the cosmic acceleration is even more violent than we have dared to suppose? There exists a theoretical specter known as phantom energy, a form of dark energy so potent and bizarre it makes the previous ideas seem almost tame. Here, the equation of state parameter, that critical number describing the energy's pressure, does not just equal -1 or hover near it, it plunges to a value less than -1. This small numerical shift has catastrophic consequences. While the cosmological constant and quintessence push the universe apart, phantom energy would make the expansion rate grow infinitely over time. The repulsive force would not just continue, it would strengthen without any limit. The ultimate fate this model predicts is the most dramatic of all, an event cosmologists call the Big Rip. Imagine the accelerating expansion growing so powerful that it overwhelms every single force that holds the universe together. First, the cosmic scales where gravity rules would be dismantled. The delicate gravitational glue binding clusters of galaxies would fail, sending these island cities flying off into the void. As the acceleration intensifies, individual galaxies would be next. The Milky Way and all its stars would be torn asunder, no longer able to resist the phantom force ripping space itself apart from within. Then it would come for our solar system. Planets would be wrenched from their orbits, flung into the endless, darkening expanse. In the final moments, the terror would become personal. The phantom energy's grip would grow stronger than the forces binding atoms together. Stars and planets would be shredded. Every molecule, every atom, every atomic nucleus in your body would be violently pulled apart. In the end, the very fabric of space-time would be torn to pieces, leaving a desolate, disconnected void where a universe once was. This is not a slow fading, but a violent, ultimate dissolution of reality. Is such a scenario possible? Current observations suggest our universe's dark energy parameter is very close to -1, but the error bars in our measurements leave a tiny, haunting window open for a value less than -1. While the data currently favors the simpler cosmological constant, the mere possibility of phantom energy forces us to confront the most extreme potential of the missing energy that surrounds us. It asks a chilling question: are we living in a cosmos that will expand forever in quiet solitude, or one that is destined for a final, self-inflicted annihilation? Perhaps the answer to our missing matter problem is not an invisible substance, but a fundamental error in our understanding of gravity itself. This is the radical proposition of modified Newtonian dynamics, or MOND. For centuries, we have relied on Newton's laws and Einstein's general relativity to describe how gravity works. These theories are spectacularly successful, predicting the orbit of planets and the bending of starlight with incredible precision. But what if these laws break down under certain conditions? MOND suggests that on the vast, diffuse scales of galaxies, our equations for gravity are subtly wrong. The theory was born from a single, stubborn anomaly: the rotation of galaxies. According to Newtonian physics, stars on the outer edges of a spiral galaxy should orbit more slowly than those near the center, just as Pluto orbits the Sun much slower than Mercury. Yet when astronomers measured these rotations, they found something shocking. The outer stars were moving just as fast as the inner ones. The galaxy was rotating so quickly that it should have flown apart. The conventional solution is to propose a massive halo of dark matter, providing extra gravitational glue to hold the galaxy together. MOND offers a different fix. It proposes a tiny modification to Newton's second law of motion, but only at extremely low accelerations, the kind experienced in the deep quiet of a galaxy's outskirts. In this regime, gravity becomes slightly stronger than expected. This single tweak perfectly reproduces the flat rotation curves of galaxies without needing any dark matter at all. It is an elegant solution that cures the immediate symptom. Think of it like this: you have a car that mysteriously gains speed when you take your foot off the gas. The dark matter approach is to say an invisible force is pushing it. The MOND approach is to suggest that the laws of friction themselves work differently at very low speeds. The appeal is powerful: a universe governed by known physics without a phantom component making up most of its mass. Yet for all its elegance on the galactic scale, MOND faces immense challenges when confronted with the rest of the cosmos. It struggles to explain the behavior of massive galaxy clusters, where the observed gravitational lensing, the bending of light by gravity, is so strong it implies far more mass than MOND can account for. The theory also fails to explain the precise pattern seen in the cosmic microwave background, the ancient light from the Big Bang. The peaks and troughs in this radiation are a detailed blueprint for the early universe, and they match simulations that include dark matter almost perfectly. A modified gravity theory alone has not yet been able to reproduce this cosmic fingerprint, so we are left with a deep puzzle. Is the universe filled with a mysterious, invisible substance that we cannot yet detect? Or have we been fundamentally mistaken about the force that literally holds our world together? This is not just a debate about missing matter, but a question that strikes at the very laws we use to define reality. What if dark matter and dark energy are not two separate mysteries, but two faces of the same cosmic entity? This is the elegant, almost poetic proposal of the Chaplygin gas model. It dares to suggest that a single, exotic fluid permeates the cosmos, a substance that changes its character over the eons to play both roles in the cosmic drama. In the dense, crowded universe of the distant past, this fluid would have clumped together under gravity, acting just like the invisible scaffolding of dark matter, helping to pull galaxies and clusters into existence. Then, as the universe expanded and thinned out, this very same substance would have undergone a profound transformation. Its pressure would have turned negative, generating a repulsive force that began to dominate the cosmos, behaving exactly like the dark energy that accelerates the expansion today. It is a cosmic chameleon, a unified solution that would beautifully simplify our inventory of the unknown. To grasp this, picture a strange, universal atmosphere. In the youth of the universe, this atmosphere was thick and heavy, settling into the valleys of space-time to form the gravitational wells that galaxies would later form within. But as the universe aged and this atmosphere became more diffuse, it changed. It began to push back, exerting a gentle but relentless pressure that now inflates the cosmos. This is the promise of the Chaplygin gas, a single answer to both of our biggest questions. Yet for all its conceptual elegance, this model faces a formidable challenge. The way galaxies and the vast cosmic web are structured today presents a serious problem. When physicists run simulations of the universe with a Chaplygin gas, they often find that this unified fluid is almost too smooth. It struggles to create the specific, clumpy distribution of matter that we observe etched across the sky in the form of galaxy clusters and immense voids. The dark matter in our standard models is cold and slow, allowing it to collapse into the dense halos that galaxies need to form. The Chaplygin gas can be more stubborn, sometimes resisting the level of clustering required to build the universe we see. So we are left with a compelling but contested idea. Is the cosmos governed by two separate, unknown components, or is it shaped by one fluid with a split personality? The search for an answer pushes at the very limits of our cosmic models. Our quest for the universe's missing energy now ventures into one of the most profound and bizarre ideas in all of physics. The holographic principle proposes that our reality, with its rich three-dimensional depth, might be nothing more than a magnificent illusion. According to this radical theory, the universe we perceive is a holographic projection, a cosmic mirage generated from a two-dimensional surface that exists at the very boundary of space. All the information required to describe every galaxy, every star, and every one of us is encoded on this distant, flat shell, like the data etched onto a Blu-ray disc. The three-dimensional world we move through is just a vast, dynamic read out of that information. This concept emerges directly from the study of black holes, where physicists discovered a startling fact. The maximum amount of information that can be stuffed into any region of space is not proportional to its volume, as you might expect, but to the area of its surface. It is as if a vast library, every book you have ever read, could be perfectly described by just the titles and authors listed on its front door. This single, counterintuitive rule suggests that the true, fundamental degrees of freedom of the universe are painted on a two-dimensional canvas. So, what does this have to do with dark energy? The connection lies in the nature of this cosmic projection. If our reality is a hologram, then the force we call dark energy, the driver of cosmic acceleration, might not be a substance or a field in the traditional sense. It could be a consequence of the way information is processed and projected from the underlying two-dimensional code. The energy of the vacuum, that stubborn cosmological constant, might simply be a side effect of the universe running its cosmic software, with the projection process itself generating the repulsive force we observe. This transforms the mystery of dark energy from a search for a missing ingredient into a question about the fundamental resolution of our reality. Are we living inside a universe that is, at its heart, profoundly two-dimensional? The holographic principle does not yet offer a complete, testable theory, but it provides a breathtaking new lens through which to view the cosmos. It dares to suggest that the ultimate nature of reality is not matter or energy, but information itself. The holographic universe suggests our reality might be written on a flat surface, but another idea proposes the secret is hiding in plain sight, within the very concept of nothingness itself. This is the enigma of vacuum energy, a prediction that empty space is not empty at all. According to quantum field theory, the vacuum is a chaotic sea of activity. So-called virtual particles are constantly flickering in and out of existence, borrowing energy from the void for impossibly brief moments before annihilating each other. This endless dance of creation and destruction is not just theoretical. we can observe its effects in the lab, such as the slight shift in the energy levels of atoms known as the Casimir effect. This perpetual motion means that empty space should be brimming with a fundamental energy, a baseline jitter that permeates every cubic centimeter of the universe. This vacuum energy presents a perfect candidate for Einstein's cosmological constant, the very force driving cosmic acceleration. It seems like a perfect fit, a seamless explanation for dark energy born from our most fundamental laws of physics. But here we encounter what is often called the worst prediction in the entire history of science. When physicists calculate the expected density of this vacuum energy, the number they get is absurdly, incomprehensibly large. The theoretical value is a staggering 120 orders of magnitude greater than the tiny, gentle repulsion we actually observe. 120 orders of magnitude. To grasp that scale, consider that the number of atoms in the entire observable universe is only about 80 orders of magnitude. Our prediction is off by a factor that is more than a trillion times larger than the entire cosmos. This is the cosmological constant problem in its full, embarrassing glory. The vacuum should be so densely packed with this repulsive energy that the universe would have been torn apart in the first instance of the Big Bang, never allowing a single atom, let alone a galaxy or a planet, to form. Yet here we are, in a cosmos that expanded gently for billions of years before acceleration even began. This is not a small rounding error. It is a fundamental crisis, a screaming contradiction between our two most successful pillars of physics, quantum theory and general relativity. One tells us the vacuum must have a colossal energy, while the other, combined with our observations, shows us a universe that is almost perfectly flat and calm. So we are left with a haunting question. Is our understanding of the quantum vacuum completely wrong? Or is there some mysterious, perfect cancellation mechanism that almost but not entirely zeroes out this immense energy, leaving behind just the faintest whisper we call dark energy? The void is not silent. It is roaring with a power we cannot explain. This staggering mismatch between prediction and reality is the cosmological constant problem, a flaw so deep it threatens to unravel modern physics. Our two most powerful theories are screaming two different truths. Quantum field theory, which governs the microscopic world, insists that the vacuum of space must be seething with an unimaginable density of energy. Yet our telescopes peering into the cosmic vastness see a universe whose expansion is only gently accelerating, driven by a dark energy value that is almost zero. The number is so tiny it is like predicting a tidal wave capable of drowning the entire cosmos, and instead finding only a single, gentle ripple in a vast, still ocean. One possible solution lies in the elegant mathematics of supersymmetry. This theory proposes that every known particle has a hidden superpartner twin. For every electron, there would be a hypothetical selectron. For every quark, a squark. The beauty of this idea is that the quantum jitters of these particle pairs could perfectly cancel each other out. The frantic, positive energy contributions from ordinary particles would be exactly balanced by the negative contributions from their supersymmetric shadows. This would drive the net energy of the vacuum down to zero, solving the problem in one grand theoretical sweep. But there is a catch. If supersymmetry is real, we should have found evidence for these partner particles in our most powerful colliders by now. So far, we have not. This leaves another, more philosophical answer on the table, the anthropic principle. This controversial idea suggests that the value of the cosmological constant is not dictated by a fundamental law, but is instead a random, environmental variable. In this picture, our universe is just one bubble in an infinite, bubbling multiverse. In the overwhelming majority of these universes, the cosmological constant is indeed enormous, and those cosmos are either ripped apart instantly or collapse back on themselves before anything can form. But in a vanishingly rare subset of universes, by pure chance, the constant is minuscule, and only in those exceptionally calm and finely tuned universes can galaxies, stars, planets, and ultimately conscious observers like us ever arise. We are not here because the laws of physics demanded this specific value. We are here because only in a universe with this specific value could anything be here at all. So is the answer a beautiful symmetry we have yet to discover, or a cosmic lottery ticket we just happen to draw? The silence from our particle colliders is making the latter, more existential possibility increasingly difficult to ignore. That profound silence from our particle colliders forces us to confront a truly cosmic possibility. Perhaps the universe is not fine-tuned for life by any fundamental law, but we are simply the lucky winners of a cosmic lottery. This is the essence of the anthropic principle, a concept that moves the mystery from physics into the realm of sheer statistics. Imagine a near-infinite multiverse, a frothing sea of reality bubbles, each with its own random set of physical laws and constants. In the vast majority of these universes, the value of the cosmological constant is enormous. Those universes are catastrophic failures. If the dark energy is too strong, space tears itself apart in a violent flash, never forming a single atom. If it is too negative, the universe collapses back into a big crunch before the first star can ignite. But in an incomprehensibly rare subset of these bubbles, by pure chance, the dial lands on a value very close to zero. Only in these exceptionally calm and stable pockets can matter coalesce, stars burn for billions of years, and planets provide a stage for life to emerge. We find ourselves in such a universe not because it is special, but because it is one of the very few where the question can even be asked. The anthropic principle finds a startlingly concrete home in the mathematics of string theory. For decades, physicists hoped string theory would provide a single, unique equation describing our universe. Instead, they discovered a landscape of staggering proportions. The theory allows for a colossal number of possible stable configurations, perhaps 10 to the power of 500 or more. Each of these configurations corresponds to a different universe with its own distinct values for fundamental constants, including the strength of dark energy. Our cosmos, then, is not the universe but merely one garden in an endless branching vineyard. This landscape is populated by a process called eternal inflation. Picture the primordial vacuum as an energy field desperate to decay. It does so by bubbling, with new universes spontaneously nucleating within the inflating background, each one a separate pocket reality with randomized laws. We are living inside one of these bubbles. In this grand picture, the tiny, non-zero value of our dark energy is no longer a puzzle to be solved by a single equation. It is simply our local address. It is the environmental condition of our specific cosmic neighborhood, one that allowed galaxies and observers to form. So the question shifts. We are no longer asking why the laws of physics are what they are. We are asking why we find ourselves in the part of the multiverse where the laws allow for our existence. The answer is as simple as it is humbling. We could not be anywhere else. But what if one of physics' most sacred constants is not so constant after all? For over a century, the speed of light has been the ultimate cosmic speed limit, a fixed number woven into the very fabric of our physical laws. Yet a handful of physicists dare to ask a heretical question. What if the speed of light was different in the distant past? Theories proposing a time-varying speed of light, or VSL, suggest that in the universe's first fleeting moments, light traveled at a rate exponentially faster than it does today. This is not a minor adjustment. It is a rewrite of cosmic history that aims to solve some of cosmology's deepest puzzles. Consider the horizon problem. The cosmic microwave background, the oldest light we can see, shows a remarkably uniform temperature in every direction we look. But according to standard cosmology, these distant regions of the sky were never in causal contact. They were too far apart for light or heat to have traveled between them, even in the entire age of the universe. It is as if you walked into a room where every corner had settled to the exact same temperature, yet the heaters had never communicated. The standard fix is a brief period of ultra-fast expansion called inflation. But VSL offers a radical alternative. If the speed of light was nearly infinite at the beginning, then information and energy could have crisscrossed the entire infant cosmos in an instant, smoothly ironing out all the temperatures and creating the uniformity we observe today. This varying speed of light could also resolve the flatness problem. Our universe appears incredibly flat on large scales, a delicate balancing act that requires its initial expansion rate and energy density to be fine-tuned to an astonishing degree. A faster speed of light in the early universe would have naturally driven the cosmos toward this flat geometry, making the perfect balance we see not a lucky accident but an inevitable outcome. So where does dark energy fit into this? If the speed of light is slowly changing even now, this gradual evolution could manifest as an apparent acceleration in the expansion of the universe. The effect we measure and call dark energy might not be a new force at all, but a subtle shadow cast by a fundamental constant in slow decay. We would be misreading a change in the rules of the cosmic game as a new player on the field. The challenge, of course, is evidence. The constancy of the speed of light is a cornerstone of modern physics, backed by a vast web of experimental results. Any theory that challenges it must make a bold, testable prediction that distinguishes it from the standard model. While no conclusive proof exists, the idea forces us to confront the very nature of the laws we hold as immutable. Are the constants of nature truly fixed for all time, or are they merely the current settings in an evolving cosmos? The answer could change everything we know about the universe's missing energy. Eric Verland proposes a truth so fundamental it redefines gravity itself. He suggests that gravity, the force that sculpts galaxies and holds our feet to the ground, is not a fundamental ingredient of the universe. It is an emergent phenomenon, a side effect of something more primal. In this view, gravity is not a force that travels through space, but a statistical tendency, much like how the pressure in a gas emerges from the collective jostling of countless invisible molecules. It is an illusion born from the way information is stored and processed on the cosmic scale. The source of this illusion, Verland argues, is entropy. We usually think of entropy as a measure of disorder, but in its deepest sense, it is a measure of hidden information. Every object, from a planet to a person, carries an amount of information associated with it. According to the holographic principle, that information is not stored within the object's volume, but is encoded on a distant, theoretical surface called the cosmological horizon, the ultimate boundary of the observable universe. When an object like a star moves, it displaces information on this cosmic screen. Verland's masterstroke was to show that this displacement of information creates a force that behaves exactly like gravity. It is a cosmic version of a phenomenon called entropic force. A simple analogy can help. Think of a single polymer chain, a long, floppy molecule floating in water. If you try to squeeze this chain into a tight ball, you are not fighting a fundamental force of compression. You are fighting entropy. The chain naturally wants to explore all its possible floppy configurations, and resisting this tendency feels like a repulsive push. In Verland's universe, what we perceive as the attractive pull of gravity is a similar effect, but in reverse. The universe naturally tends toward states of higher entropy, and the movement of mass creates an entropic gradient that draws objects together. This is not a force in the traditional sense, but a statistical drift toward cosmic disorder. So, where does dark energy fit into this radical picture? In Verland's emergent gravity, the accelerated expansion of the universe is not driven by a mysterious substance with negative pressure. Instead, it is a natural consequence of the universe's evolving information content. As the cosmos expands, the amount of information that can be stored on the cosmological horizon increases. This growth in the universe's information budget fundamentally changes the equations for gravity on the largest scales. The extra information associated with dark energy, the energy of empty space, generates an additional entropic force that manifests as cosmic repulsion. In essence, the universe's accelerating expansion is the result of its own memory filling up. The beauty of this idea is its unification. It does not add a new, unexplained component to the cosmic inventory. Instead, it suggests that both gravity and dark energy are two different manifestations of the same underlying process, the relentless drive of the cosmos toward higher states of entropy and information. The gravitational pull we feel and the cosmic push we observe are simply two sides of the same entropic coin. The theory is still in its infancy, and it faces significant mathematical and observational hurdles, but it offers a breathtakingly different perspective. It asks us to consider that the force that guides the planets might be nothing more than a cosmic mirage, a ghostly echo of the universe remembering itself. Einstein's theory of general relativity has been our most reliable guide to the cosmos for over a century, but what if its equations are not the final word? A powerful class of theories suggests we need only tweak the cosmic rulebook to explain the universe's accelerating expansion. This approach is known as F of R gravity, where the R stands for the Ricci scalar, a mathematical measure of how severely spacetime is curved by the presence of mass and energy. In Einstein's original equations, this curvature term appears in a beautifully simple, linear form. But F of R gravity proposes that the relationship is more complex, that the gravitational action depends on a function of this curvature, not just the curvature itself. It is as if we have been using a straight ruler to measure a subtly warped surface, and now we are finally crafting a ruler that bends to match the true shape of reality. This single mathematical adjustment has profound consequences. Under the right conditions, an F of R function can generate a repulsive gravitational effect on cosmic scales. In the vast, low-density emptiness between galaxies, where the fabric of spacetime is only gently curved, this modified gravity would produce a natural push, driving galaxies apart at an accelerating rate. There is no need to invent a mysterious dark energy filling the void, because the acceleration emerges directly from the new geometry of gravity itself. Think of it like a strange new property of rubber. Imagine a rubber sheet representing spacetime. In Einstein's universe, a heavy ball placed on the sheet creates a dip that pulls other objects inward. But in an F of R universe, the rubber itself has a hidden springiness. When the sheet is stretched over immense distances, this springiness causes it to expand on its own, gently pushing the balls apart. The force driving the cosmos apart is not an external energy, but an inherent property of the stretched spacetime fabric. This elegant idea is not without its own tight constraints. For an F of R theory to be viable, it must pass all the same tests that general relativity has aced over the decades. It must perfectly account for the precise orbit of Mercury, the bending of light around the Sun, and the timing of signals from distant pulsars. Crafting a function that explains cosmic acceleration while remaining invisible in our solar system is a monumental challenge. The ghost of dark energy is a tough one to exercise. So we are left with a compelling fork in the theoretical road. Do we preserve Einstein's equations and populate the universe with an unknown, dominant energy? Or do we rewrite the laws of gravity themselves to make the acceleration a natural feature of the cosmos? The choice could not be more fundamental. This idea of rewriting gravity leads us to a cosmos of far greater dimensions. String theory whispers of a reality where our universe is merely a single slice of a much grander structure. This is the brain world scenario, Our entire four-dimensional space-time, with its 3 dimensions of space and 1 of time, could be a 3-dimensional membrane or brain floating within a higher dimensional expanse called the bulk. Every galaxy, every star, and every one of us would be permanently stuck to this membrane like dust particles trapped on the surface of a soap film. The forces we know and love, like electromagnetism and the nuclear forces, are like glue binding us to the brain, unable to escape into the wider bulk. But gravity is different. Gravity, being the geometry of spacetime itself, might be the one force that can leak away. It could be spreading out into the extra dimensions, diluting its strength as it travels through the bulk. From our perspective on the brain, this leakage would make gravity appear weaker than it truly is, offering a potential explanation for why it is so fantastically feeble compared to the other fundamental forces. But how does this connect to the cosmic acceleration we call dark energy? The answer lies in the dynamics of the brain itself. Our membrane universe may not be static and rigid. It could be vibrating, stretching, or even interacting with other parallel brains floating in the bulk. A gentle, universal tension in our brain, a constant pull trying to contract it, could be balanced by a pressure from within the brain's own energy fields. This delicate balance could generate a repulsive effect on cosmological scales, perfectly mimicking the behavior of dark energy and driving the expansion of our 3-dimensional space. Another possibility involves a 5th-dimensional phenomenon. If the bulk itself is expanding, our brain would be forced to expand with it. The acceleration we measure would not be driven by an internal energy, but would simply be a consequence of our entire reality being stretched by the growth of the higher dimensional space it is embedded within. We would be like ants on the surface of an inflating balloon, perceiving the stretching of our 2-dimensional ground as a mysterious force, unaware of the 3rd dimension causing it all. The beauty of this model is its unification of puzzles. It can potentially explain the hierarchy of forces, the nature of gravity, and the mystery of dark energy under one breathtaking roof. Yet it comes with a profound cost. If this is true, then the true nature of reality exists in a space we cannot see, touch, or directly explore. We are confined to our cosmic island, forever inferring the shape of the greater ocean from the strange tides that wash upon our shores. While gravity may leak into other dimensions, the quantum vacuum holds its own bizarre power, one we can actually measure in a laboratory. 2 perfectly smooth, neutral metal plates placed almost impossibly close together in a vacuum will spontaneously pull toward each other. This is the Casimir effect, a confirmed phenomenon that proves empty space is not empty. It is a seething ocean of virtual particles, constantly flickering into and out of existence. These fleeting quantum fluctuations have a characteristic wavelength. When the plates are brought very close, only the tiniest wavelengths of virtual particles can fit in the narrow gap between them. Outside the plates, however, virtual particles of all wavelengths can appear. This imbalance creates a subtle pressure differential, pushing the plates together with a force that can be precisely calculated and measured. The space between the plates has a lower energy density than the space outside. In a profound sense, the region between the plates possesses a kind of negative energy relative to the bustling vacuum around it. This is not just a theoretical curiosity. It demonstrates that we can, in principle, engineer the energy density of the vacuum, creating pockets where the frantic quantum activity is partially suppressed. So what does this mean for the cosmos? If we can create a relative negative energy density in a lab, could nature produce an absolute version on a cosmic scale? Some theorists speculate that such configurations of negative energy could be the key to stabilizing wormholes, those hypothetical shortcuts through spacetime. More pertinently, the properties of this vacuum energy are exactly what drives the cosmological constant. The Casimir effect gives us a tangible, experimental handle on the very type of energy that seems to be accelerating the universe. Yet it also highlights the colossal gap in our understanding. the energy density we manipulate in the Casimir effect is minuscule, while the predicted vacuum energy from quantum field theory remains impossibly large. This real-world phenomenon grounds our most abstract cosmic mystery in a force you can almost touch, a silent whisper of attraction between two metal plates that speaks volumes about the hidden structure of reality. Redshift is the foundational clue for an expanding universe, but what if we have misread this cosmic signal? The tired light hypothesis proposes a radically different cause. Instead of galaxies flying away from us within stretching space, this idea suggests that light simply loses energy on its long journey across the cosmos. As photons travel for billions of years, they might interact with a diffuse interstellar medium or some unknown field, gradually shifting their wavelength toward the red end of the spectrum. In this picture, the universe could be static and eternal, with the redshift we observe having nothing to do with velocity or expansion. It is a compellingly simple alternative, one that does away with the need for a big bang or dark energy. Light is not Doppler shifted by recession, it is just tired. The appeal is immediate, a universe that does not require a definitive beginning or a mysterious accelerating end. Yet for decades, this idea has been largely dismissed, and for a critical reason. If light is truly losing energy to some form of interstellar fog, the interaction should also scatter the light, blurring the images of distant galaxies and quasars. We would expect faraway objects to appear fuzzy and distorted, like a street lamp seen through a thick fog. Our most powerful telescopes, however, see something very different. The light from ancient supernova and remote quasars arrives sharp and clear. There is no evidence of the scattering that a simple tired light mechanism would produce. This observational fact has been a decisive blow to the classical model. But science evolves, and modern variations of the concept have emerged, attempting to sidestep this fatal flaw. Some theorists propose more sophisticated mechanisms where light interacts with virtual particles of the quantum vacuum in a way that causes a redshift without significant scattering. Another idea suggests that the photon's energy loss is not due to a collision, but a fundamental property of spacetime itself, a gradual decay over extreme distances. Could these refined versions challenge our interpretation? The answer still lies in other, independent tests. In an expanding universe, the redshift is coupled with a phenomenon called time dilation. The light from a distant supernova should not only be redshifted, but the duration of its brightening and fading should appear stretched out from our perspective, because the expanding space is stretching the very fabric of time along with the light. And this is exactly what we observe. The light curves of faraway supernova are measurably longer than those of nearby ones, a simple tired light model where only the photon's energy is sapped cannot produce this temporal stretching. The light would be redder, but the clock of the event would tick at the same rate. The fact that we see time dilation is a powerful, independent confirmation that we are indeed witnessing the effects of an expanding spacetime fabric, not just a loss of photon energy. So while the tired light idea challenges us to question our assumptions, the collective weight of the evidence solidifies the expansion paradigm. The redshift is not a sign of fatigue, but the unmistakable signature of a cosmos in motion, a relentless stretch that itself points toward a deeper mystery still waiting in the void. The cosmos might not have a single, definitive beginning. Instead of a solitary Big Bang, our universe could be caught in an endless, rhythmic dance of creation and destruction. This is the cyclic model, where the history of everything is a series of colossal collisions between our world and another, a process that erases the past and begins the future anew. In this breathtaking picture, our entire three-dimensional reality is a brain, and its cosmic twin floats parallel to us in a hidden, higher-dimensional bulk. For most of the cycle, these two brains are slowly drifting apart, their separation driving what we perceive as the expansion of our own space. Galaxies form, stars burn, and life emerges, all while the gap between our world and its mirror widens. But this expansion does not continue forever. Dark energy is the critical engine of this eternal return. Its gentle, repulsive push ensures the universe expands enough to dilute all the accumulated entropy, the cosmic disorder that builds up over eons. It flattens and cools the cosmos, wiping the slate clean and preparing it for the next act. Once the universe is sufficiently vast, empty, and smooth, the attraction between the two brains takes over. They begin to move toward each other, accelerating through the bulk until they collide. That collision is not an end, it is a new Big Bang. The immense kinetic energy of the impact is converted into a firestorm of radiation and matter, flooding our brain with heat and restarting the cosmic clock. The universe is reborn, hot and dense, but without the baggage of its previous incarnation. All the black holes, all the scattered stardust, all the history of the previous cycle is scoured away by the sheer energy of the collision. This cyclic model, sometimes called the ekpyrotic universe, offers a profound answer to the question of our beginning. We are not living in the first and only universe, but in one iteration of an infinite series. Dark energy is no longer a mysterious force leading to a cold, lonely end. It is the cosmic custodian, the essential agent that stretches the universe to a pristine state, making each new collision and each new birth possible. It transforms the cosmos from a one-act play into an eternal symphony of fire and ice. Our invisible universe might be shaped by ghosts that pass through our bodies by the trillions every second. These are neutrinos, the most elusive and abundant massive particles we know of. Born in the nuclear fires of stars and the cataclysmic violence of supernova, they flood the cosmos, barely interacting with anything at all. For a long time, we thought they were massless, moving at the speed of light and carrying no weight in the cosmic ledger, but physics had a surprise in store. Neutrino oscillation experiments revealed that these phantoms do, in fact, have a tiny, almost imperceptible mass. This discovery opened a tantalizing possibility. Could these ethereal particles form a background sea of hot dark matter, subtly influencing the grand architecture of the cosmos? The key is in their temperature and speed. Hot dark matter refers to particles that were moving at velocities close to the speed of light when the first structures in the universe began to form. This incredible speed makes them resistant to clumping under gravity on small scales. They would have streamed freely out of any nascent cosmic structures, effectively ironing out the wrinkles in the universe before they could grow into galaxies. This is why neutrinos alone cannot be the primary component of dark matter. The cosmic web of clusters and filaments we see today was clearly built by cold, slow-moving dark matter that could collapse effectively. Yet, the gravitational influence of a vast sea of hot neutrinos is not zero. Their combined mass, spread uniformly across the universe, contributes to the overall density of the cosmos. This affects the expansion rate of the universe over its entire history. Even a small mass per neutrino, when multiplied by the staggering number of them in existence, adds up to a significant component of the cosmic energy budget. More intriguingly, some theories suggest that the peculiar properties of neutrinos could intertwine with the mystery of dark energy. Certain models propose that neutrinos, with their ability to flip between different types or states, might have a small, varying interaction with the field responsible for cosmic acceleration. In one era, they might behave like ordinary particles, and in another, their unique quantum nature could amplify or modify the effects of the dark energy field. Imagine a cosmic feedback loop where the evolving density of neutrinos as the universe expands subtly tweaks the behavior of the force pushing it apart. While they are not the sole answer to the missing energy problem, neutrinos represent a crucial piece of the puzzle. They are a known, yet poorly understood, component that sits at the intersection of the particle world and the cosmic scale. Their ghostly presence reminds us that the solutions to our greatest mysteries may not lie in one single, monstrous discovery, but in the delicate interplay of countless subtle forces. A perfectly smooth universe is the bedrock of modern cosmology, but this very assumption could be the source of our greatest error. The cosmos we observe is not a featureless soup. It is a tapestry of immense galaxy clusters, sprawling filaments, and correspondingly vast, empty voids. The inhomogeneous universe model dares to ask a simple yet revolutionary question. What if our entire galactic neighborhood, including the billions of galaxies we can survey, sits inside one of these colossal voids? This single shift in perspective could rewrite the story of dark energy. According to Einstein's general relativity, gravity behaves differently in empty regions compared to dense ones. Matter warps space-time, and the density of that matter dictates how space itself expands. Inside a giant underdense void, the local expansion rate would be faster than the cosmic average. There is less gravitational pull from matter to slow things down, so space within the void stretches more quickly. Now, imagine we are astronomers living inside this bubble, trying to measure the expansion of the entire cosmos. When we look out at distant supernova, their light has traveled through both the dense walls of the cosmic web and our local, fast-expanding void. The path that light takes and the expansion it experiences along the way are not uniform. The peculiar gravitational landscape can subtly alter the light's journey, affecting how we perceive its redshift and its apparent distance. From our vantage point deep inside the bubble, it could look exactly as if the whole universe is accelerating. The dimming of those faraway supernova, the very observation that won the Nobel Prize for dark energy, might not be due to a mysterious repulsive force. It could be a grand illusion, a cosmic mirage created by our unfortunate location in a relative desert. Think of it like standing in a valley and trying to judge the slope of the entire continent. From your low position, the surrounding hills might appear much higher and steeper than they truly are, distorting your perception of the overall landscape. If this model is correct, dark energy vanishes. The acceleration is not a fundamental property of the universe, but a local observational effect. The energy budget of the cosmos would be radically different, and we would need no mysterious component to explain the observations. The challenge, of course, is evidence. Can a void large enough and empty enough to produce this illusion actually exist? The model requires a void of staggering proportions, hundreds of millions of light years across, which would itself be a highly unusual structure. Furthermore, such a model must also perfectly reproduce all the other evidence for dark energy, including the precise patterns in the cosmic microwave background. While the standard model of cosmology still fits the data best, the inhomogeneous universe idea remains a powerful and persistent challenge. It forces us to confront a profound and humbling possibility. The greatest mystery in physics might not be a missing energy, but a simple error of cosmic perspective. Could the collective gravity of every galaxy and cluster be secretly steering the cosmos? This is the provocative idea behind back reaction, a theory that suggests we have been looking at the universe the wrong way. For a century, we have modeled the cosmos as if it were a perfectly smooth fluid, a uniform soup of matter and energy where every region is essentially the same. This simplification makes the math of general relativity manageable, but it ignores a glaring reality. Our universe is profoundly lumpy. It is a web of dense galaxy clusters, long filaments, and enormous, nearly empty voids. The back reaction theory proposes that this very lumpiness, the gravitational pull of all these structures as they form, creates a feedback effect that changes how the entire universe expands. When matter collapses to form a galaxy cluster, it creates a deep gravitational well. This process does not just affect the local area. The energy involved in this cosmic structuring subtly influences the average expansion rate across the whole universe. Think of a calm ocean. If you were to measure its average surface level from a satellite, you would get one number. But if you were to somehow erase all the waves and ripples, the average level might actually be slightly different. The act of smoothing out the ocean changes your measurement of it. In a similar way, by mathematically smoothing out the universe's lumps to apply Einstein's equations, we might be creating the illusion of dark energy. The acceleration we measure could be a consequence of this averaging process, a cosmic mirage generated by the intricate gravitational landscape we call home. The empty voids play a particularly powerful role. As the universe evolves, these voids grow and merge, becoming ever larger and emptier. With very little matter inside, their internal expansion is faster than the cosmic average. Since voids now make up most of the volume of the universe, their faster expansion could be dominating the global measurement, making it appear as if everything is accelerating. From our vantage point inside a galactic filament, we are not seeing a true, uniform acceleration, but the statistical outcome of being surrounded by an ocean of rapidly stretching nothingness. This idea turns the standard story on its head. Dark energy would not be a mysterious substance, but an emergent property, a collective effect of the universe's complex structure. The challenge for this theory is formidable. It must prove that this backreaction effect is strong enough to completely mimic the observed acceleration, a task that requires immensely complex calculations beyond our current computational power. While the evidence still strongly favors a fundamental dark energy, the backreaction concept serves as a crucial reminder. The universe is not a simple place, and the greatest secrets may be hidden not in what we have missed, but in the overlooked consequences of what we already see. Hidden deep within the mathematical heart of physics might be a sector of reality operating by rules so alien they defy our very concept of a particle. This is the realm of unparticle physics. It proposes that our familiar universe of quarks, electrons, and photons is just one part of a much larger picture. Alongside it exists a hidden sector governed by a theory with scale invariance. This means it looks the same no matter how much you zoom in or out, having no fixed mass scales or typical sizes. The stuff of this sector is not made of distinct particles, but of what theorists call unparticles, entities that behave more like a continuous, ethereal substance than discrete bits of matter. Imagine trying to describe a cloud. You would not list individual, identical water droplets with specific properties. Instead, you would describe its overall density, its texture, its behavior as a whole. Unparticles are the clouds of the particle world, a smeared-out, non-particulate existence. So how could this ghostly sector affect our cosmos? The proposal is that this unparticle stuff interacts with our familiar world, but only very feebly, primarily through gravity. It does not clump into galaxies or planets. It would permeate all of space as a smooth, continuous background, a cosmic ether with its own unique energy signature. Because of its scale-invariant nature, its energy density would evolve in a very specific way as the universe expands, potentially mimicking the behavior of dark energy. It would produce a gentle, persistent repulsion that accelerates the cosmic expansion, not as a cosmological constant, but as the inherent property of this hidden dimension of reality. The appeal of this idea is its sheer novelty. It does not modify gravity or add a new field to our existing model. Instead, it proposes an entirely new layer of physics, one that has been invisible to our experiments because it speaks the language of gravity alone. Detecting this would require the most subtle gravitational measurements, perhaps by observing the precise timing of signals from pulsars or by mapping the cosmic microwave background with even greater precision, searching for the faintest imprint of this unparticle whisper on the fabric of spacetime. The theory remains highly speculative, a fascinating what-if on the frontier of knowledge. It challenges us to ask if the vacuum of space is not just filled with quantum flickers, but with something far more strange and structured, a hidden ocean of unparticles whose subtle tide is pushing the galaxies apart. Black holes might be growing in the dark, their mass swelling not from devouring stars, but from the stretching of space itself. A radical new idea suggests these gravitational monsters are cosmologically coupled, gaining mass as the universe expands. This isn't about the gas and dust they consume, but a direct, profound link between the vacuum of space and the heart of a black hole. According to this hypothesis, the energy of the universe's expansion is somehow deposited inside the black hole's event horizon, causing its mass to increase in lockstep with the scale of the cosmos. The mathematics reveals a startling possibility. If the coupling is of a specific strength, the combined mass of all the black holes in the universe could be increasing at a rate that perfectly accounts for the observed acceleration. The dark energy driving galaxies apart wouldn't be a mysterious field, but the hidden mass accumulating in these darkest of prisons. Think of the universe as an expanding balloon with black holes like knots tied into its rubber surface. As you inflate the balloon, the knots don't just move apart, they themselves grow larger, their increased mass contributing to the overall energy required to stretch the balloon further. This turns our understanding of black holes on its head. They would no longer be passive endpoints for matter, but active, evolving components of the cosmic engine. The energy budget of the universe gets a dramatic revision, with a significant portion of the missing energy literally locked away behind event horizons, invisible to us but gravitationally potent. The controversy, of course, is fierce. Critics point out that this model relies on a specific and still debated view of a black hole's interior, and that the total mass of all known black holes seems far too small to account for all of dark energy. Yet the idea persists, a ghost in the machine of gravity, suggesting that the key to the cosmos's expansion has been hiding in its most perfect voids all along. The force of gravity itself might hold the key to the universe's runaway expansion. We have long searched for its messenger particle, the graviton, a tiny ripple in the fabric of spacetime that would carry the gravitational force just as the photon carries light. But what if this hypothetical particle is not quite what we expect? Theorists propose that gravitons could possess a vanishingly small mass. This tiny deviation from perfect masslessness would fundamentally change their nature. A massive graviton would not travel at the absolute speed of light, and its influence would have a limited range over cosmic distances. On the vastest scales, this limited reach could manifest as a gentle, repulsive pressure, a kind of gravitational fatigue that pushes the cosmos apart instead of pulling it together. Imagine the gravitational pull between two distant galaxies as a conversation. In a universe with massless gravitons, that conversation happens instantly and clearly across any distance. But if gravitons have mass, the message weakens over extreme ranges like a whisper fading across a giant hall. Over billions of light years, this faded signal could add up to a net repulsive effect, accelerating the separation of everything. Another possibility is that empty space is filled with a Bose-Einstein condensate of gravitons. In this strange state, countless gravitons would lose their individual identities and merge into a single, coherent quantum field that permeates the entire cosmos. This graviton condensate would have a constant energy density and negative pressure, behaving exactly like the cosmological constant. It would be as if the background hum of gravity's own particles, frozen into a unified quantum state, is what is actually inflating the universe. This elegant idea unifies the puzzle beautifully, suggesting that the force that binds the cosmos on small scales is also the same force that tears it apart on the largest scales. Yet the challenge is immense. Detecting a single graviton is considered nearly impossible with current technology, so proving it has mass or forms a condensate is a task for the distant future. But the mere possibility reframes our entire quest. We may not be searching for a new, exotic energy, but for a hidden property of the most familiar force in the universe. The fabric of space might be hiding a shy, cosmic chameleon, A new class of modified gravity theories proposes that a hidden field called the symmetron permeates all of reality. This is not a particle in the traditional sense, but a scalar field whose very presence and strength are dictated by its surroundings. The symmetron's behavior is governed by a cosmic game of hide and seek, with the local density of matter acting as the seeker. In the dense, crowded environments of galaxies and galaxy clusters, the symmetron field is effectively screened. It hides itself, becoming dormant and rendering its effects virtually undetectable. In these regions, Einstein's general relativity reigns supreme, and we feel only the familiar pull of gravity. This screening mechanism is the theory's brilliant escape hatch, allowing it to avoid conflict with the exquisitely precise tests of gravity we have conducted within our solar system. But venture out into the cosmic voids, the immense, empty deserts between the galaxies, and the symmetron reveals its true nature. In these low-density regions where matter is scarce, the field awakens. It turns on, acquiring a non-zero value throughout the vast emptiness, and once active, it generates a gentle, repulsive force that pushes space itself apart. In the voids, the symmetron is not hiding. It is the dominant player, and its push manifests as the very cosmic acceleration we attribute to dark energy. Think of it like a universal social force. In a crowded, noisy city square, a single whisper is impossible to hear. It is screened out by the bustle all around. This is the symmetron within a galaxy, but find yourself alone in a vast, silent desert, and that same whisper becomes the only sound for miles, clear and potent. This is the symmetron in a void, its gentle push no longer masked by the gravitational noise of matter. The beauty of this idea is its dynamic nature. Dark energy is not a uniform, static background. It is a responsive force, its strength changing based on the cosmic neighborhood. The universe accelerates not because of a fixed energy in space, but because the expanding cosmos is creating more and more void territory, areas where the symmetron can freely operate and exert its repulsive influence. This turns the cosmic acceleration into a self-reinforcing process. As the universe expands and voids grow, the symmetron's domain increases, which in turn drives more expansion. The challenge, as with all such elegant ideas, is to find its unique fingerprint. If the symmetron is real, there should be subtle, anomalous gravitational effects at the edges of galaxies, in the transitional zones where the density falls and the field begins to wake up. Future missions designed to map gravity with incredible precision will be hunting for exactly this kind of signature. The symmetron offers a universe that is not just expanding, but breathing, with a hidden field that pulses in and out of existence based on the cosmic company it keeps. Another path to cosmic acceleration hides within the mathematical elegance of symmetry, a concept named for the father of modern physics himself. The Galilean model introduces a new kind of field, a cosmic actor whose behavior is protected by a powerful principle known as Galilean invariance. This means the equations governing the field remain unchanged even if you add a constant velocity to its value, a symmetry that echoes Galileo's famous insight about motion on a ship. This specific, robust symmetry is not just a mathematical curiosity. It is the key that unlocks a universe that can self-accelerate. The Galilean field generates a repulsive force capable of driving the expansion of the cosmos, all while neatly sidestepping many of the theoretical ghosts and instabilities that plague other modified gravity proposals. It is a theory that achieves cosmic push with mathematical finesse. To grasp how this works, picture a vast, invisible fluid permeating all of space. In most models, trying to make this fluid push everything apart creates problematic ripples or instabilities that would tear structures apart. The Galilean special symmetry acts like a perfect damping system on that fluid. It allows the fluid to exert a smooth background pressure that accelerates the universe while simultaneously suppressing any wild, destructive oscillations. The field can exert immense influence on the largest cosmic scales, driving galaxies apart, yet its effects can remain cunningly hidden within our solar system. This is because the field's interactions are designed to be incredibly weak in regions of high density and strong gravity, like near the Sun or Earth. It effectively cloaks itself where it would otherwise be easily detected, passing all local tests of gravity with flying colors while still dominating the empty vastness between galaxies. The Galilean offers a universe where the force of acceleration is not a mysterious energy, but a fundamental property of a field governed by pristine symmetry. Could the same principles that describe a ball rolling down an inclined plane also hold the secret to the fate of the entire cosmos? This elegant idea challenges us to consider that dark energy might not be a thing we have to find, but a dynamic consequence of space itself, engineered by the universe's own inherent mathematical beauty. These elegant symmetries lead us to a sprawling family of possibilities, the most comprehensive frameworks for rewriting gravity known as Horndeski theories. Developed in the 1970s by physicist Gregory Horndeski, these are the most general possible theories of gravity that still include a single extra-scalar field and do not produce the ghostly instabilities that doom simpler models. They represent a vast cosmic playground, a mathematical sandbox containing every conceivable way a new, universal field could interact with spacetime itself to produce the acceleration we observe. Within this expansive landscape, four specific terms in the fundamental Lagrangian, the equation that defines a theory's dynamics, stand out with such compelling properties they have been nicknamed the Fab Four. Each term is named for a biblical figure, and each offers a unique mechanism to self-accelerate the cosmos. The John term links the new scalar field to the curvature of spacetime in a way that can produce a constant, de Sitter-like expansion, a steady push mimicking the cosmological constant. The Paul term introduces interactions that allow the field to stealthily hide its effects in regions of high gravity, like our solar system, while unleashing its repulsive power in the vast cosmic voids. The George term couples the field directly to the Einstein tensor, creating a rich dynamics that can naturally lead to an accelerating universe without a cosmological constant. And the Ringo term, while seemingly simpler, provides a crucial stabilizing influence. The power of this framework is its generality. Instead of betting on one specific model, physicists can test the entire Horndeski family at once, looking for any deviation from Einstein's predictions that falls within its allowed patterns. The most stringent tests now come not from the heavens alone, but from the most violent events in the universe, the collisions of black holes and neutron stars. When these cataclysms occur, they ripple the fabric of spacetime, sending gravitational waves across billions of light years. In Einstein's pure general relativity, these ripples travel at the speed of light. But in many Horndeski theories, the extrascalar field interacts with the gravity waves, causing them to travel at a slightly different speed. When the LIGO and Virgo observatories detected gravitational waves from a neutron star merger at the same time telescopes saw the flash of light, they confirmed that the two signals arrived virtually simultaneously after a journey of over 100 million years. This placed an incredibly tight constraint on the possible existence of many Fab Four models, ruling out a significant portion of the theoretical landscape. The hunt has now shifted to more subtle signatures, like how gravity waves might be attenuated or how their polarization could be modified over cosmic distances. The Fab Four and their Horndeski represent a path where dark energy is not a static substance, but the dynamic expression of gravity's own hidden complexity, a complexity we are just beginning to probe with the new sense of gravitational hearing. Sometimes the answers to our biggest questions are hiding in the solutions to others. For decades, physicists have hunted for a hypothetical particle called the action, not for dark energy, but to solve a deep mystery in the strong nuclear force. This ultra-light, ghostly particle is a prime candidate for the cold dark matter that binds galaxies. Yet, in a stunning twist, the very field that would produce actions might also hold the key to cosmic acceleration. Imagine a universe filled with an invisible cosmic pendulum, an action field that began oscillating at the dawn of time. In the early, dense cosmos, this oscillation was rapid and energetic, its behavior contributing to the dark matter that seeded galaxy formation. But as the universe expanded and cooled over billions of years, the pendulum swing slowed dramatically. The energy density of this oscillating field decreases in a very specific way as the cosmos ages. In some theoretical models, this slow, gentle decay does not just fade away. Instead, as the oscillation reaches a certain point in its cycle, its average pressure can turn negative. This negative pressure, stretched across the vast volume of the universe, could generate a persistent, repulsive push. It is a cosmic seesaw where the same fundamental field that once acted as clumpy, attractive dark matter has now transitioned into a smooth, repulsive dark energy. The action becomes a cosmic chameleon, playing two different roles across the immense span of cosmic history. This is not a guaranteed outcome, but a tantalizing possibility that links the two greatest mysteries in physics with a single, elegant entity. The search for the action, once the domain of dark matter hunters, now takes on a dual significance. If discovered, its specific mass and properties could reveal whether it truly has the capacity to shape the fate of the entire universe, transforming our understanding of the cosmos from its smallest particles to its largest scales. This entropic view of reality suggests that the very growth of cosmic information is what fuels the expansion. As the universe ages, its boundary, the cosmological horizon, steadily moves outward. With every new inch of space that comes into view, the surface area of this horizon increases. And since the maximum amount of information the universe can contain is proportional to this area, its total information budget is constantly growing. This is not a passive process. According to the principles of thermodynamics, systems naturally evolve toward states of higher entropy, which is fundamentally a measure of hidden information. The universe's relentless drive to maximize its entropy, to fill up its information storage capacity, might be the primary engine behind cosmic acceleration. What we call dark energy could be the thermodynamic cost of the universe remembering more. Think of the cosmos as a vast cosmic hard drive that is constantly being manufactured as it runs. The act of creating new storage space itself requires energy, and that energy manifests as a repulsive force, pushing the boundaries of reality ever outward. From our perspective within the system, this looks like a mysterious anti-gravity, a dark energy inflating the void. But from a thermodynamic perspective, it is simply the universe obeying its most fundamental tendency to evolve toward maximum disorder and information content. The gentle push separating galaxies is the universe's way of making more room for its own memories. This profound link between information, gravity, and acceleration offers a staggering unification. The same thermodynamic process that gives rise to the force we call gravity on small scales, the entropic pull that holds planets in orbit, might be responsible for the cosmic repulsion on the largest scales. It is a single, elegant mechanism expressing itself differently depending on the cosmic environment. The force that binds your feet to the ground and the force that tears clusters of galaxies apart could be two different symptoms of the same underlying cosmic law, the irresistible and universal drive toward greater entropy. A ghostly connection binds the universe, a thread of instantaneous influence that defies our intuition of space and time. This is quantum entanglement, a bizarre phenomenon where two particles, even when separated by billions of light years, remain linked in a single quantum state. A change to one is instantly reflected in the other, a coordination that seems to mock the cosmic speed limit of light. While this spooky action at a distance is a cornerstone of quantum mechanics, its implications for the cosmos at large have only just begun to be explored. Could this pervasive, invisible network of entangled links be tugging at the fabric of the universe itself? The radical proposal is that these countless quantum connections generate a tiny gravitational backreaction. Every entangled pair, from particles in distant quasars to virtual twins flickering in the void, creates a minute stress in the geometry of spacetime. On the scale of an atom, this effect is immeasurably small, utterly insignificant. But when you sum this influence over every single entangled particle across the entire visible universe, across all of cosmic history, that negligible push could accumulate into a vast collective force. It would be like the gentle pressure of a single air molecule, meaningless on its own, but when multiplied by the quintillions of molecules in the atmosphere, creating the powerful, constant push of a steady wind. This wind, blowing from the quantum realm, could be the gentle repulsion we call dark energy. The universe would not be expanding because of a new, exotic substance, but because of the gravitational hum of its own interconnectedness. The vacuum would be alive with a web of relationships, and the energy of those relationships would be slowly, inexorably pushing everything apart. This idea remains deeply speculative, a whisper from the frontier where quantum mechanics and gravity collide. Yet it offers a profoundly beautiful vision, one where the universe's acceleration is not a sign of an alien force, but the ultimate expression of a cosmos that is, at its very heart, deeply and fundamentally entangled. Our very definition of nothing is fundamentally flawed. True emptiness, a complete and utter void, does not exist in our universe. The quantum vacuum is a seething ocean of activity, a place where so-called virtual particles constantly pop into and out of existence, borrowing energy from the void for fleeting moments before vanishing. This is not just a mathematical trick, it is a physical reality confirmed by effects like the Casimir force. This vacuum energy has a specific property that is absolutely critical to the dark energy puzzle, a negative pressure. Think of the vacuum not as a calm, empty stage, but as a stretched rubber sheet. When you stretch a rubber sheet, you are putting energy into it, and the sheet pulls inward, trying to contract. This inward pull is a negative pressure. The quantum vacuum behaves in a similar way. Its intrinsic energy creates a tension, a negative pressure that, according to the equations of general relativity, generates a gravitational repulsion. This is the exact kind of effect needed to drive the accelerating expansion of the cosmos. In essence, the energy of nothingness is pushing the universe apart. Yet this elegant solution is also the source of our greatest confusion. Why is this repulsive force so incredibly weak? The calculated vacuum energy is a staggering 120 orders of magnitude stronger than what we observe. If the vacuum energy were anywhere near its theoretical value, the universe would have been torn to shreds in its first instant. So the profound question is not just about the energy of the vacuum, but about why that energy is almost but not quite zero. Is there some unknown symmetry or cancellation mechanism that almost perfectly nullifies this immense power, leaving behind only the faintest whisper, the ghost we call dark energy? The void is not empty, it is filled with a roaring potential that has been muted to a murmur, and we have no idea why. The final theory is not one of substance but of discovery itself. It is the story of how we will finally move from speculation to knowledge, using the most powerful machines ever built to read the secret history of the cosmos. Our generation stands at the threshold of a new era in cosmology, armed with a coming wave of telescopes designed to dissect dark energy with surgical precision. The Vera C. Rubin Observatory, with its colossal 3.2 billion pixel camera, will begin a 10-year survey of the sky, mapping billions of galaxies and cataloging the distances to millions of supernovae. It will measure the subtle distortions in galaxy shapes caused by dark matter's gravity, creating the most detailed chart of the cosmic web ever assembled. This immense map will reveal how the structure of the universe has grown and stretched over billions of years, allowing us to see if the strength of dark energy has changed, a telltale sign of dynamic fields like Quintessence. Following close behind, the Nancy Grace Roman Space Telescope will peer even deeper into the infrared universe. It will employ a technique called spectroscopy to precisely measure the redshifts of countless galaxies, constructing a three-dimensional view of the cosmos with unprecedented scale and accuracy. Roman will hunt for the faint imprint of Baryonian acoustic oscillations, the fossilized sound waves from the Big Bang that are frozen into the distribution of galaxies. By measuring the apparent size of these cosmic rulers at different epochs, we can track the expansion history of the universe with a fidelity that could finally distinguish between a cosmological constant and a more exotic, evolving dark energy. On the other side of the electromagnetic spectrum, the Square Kilometre Array will use a forest of radio antennas to listen to the universe. This vast instrument will detect the faint hydrogen signal from the most ancient galaxies, mapping the cosmic structure when the universe was only half its current age. By observing how these structures clump and evolve, the array will provide an independent, powerful test of gravity on the largest scales, probing for any deviation from Einstein's predictions that could point toward modified gravity theories. Together, this trio of observatories will not simply gather more data, they will perform a cosmic interrogation. They will watch the universe expand in real time across billions of years, searching for the slightest wobble in the dark energy equation of state. They will test if the acceleration is truly constant or if it holds a secret history of change. The data they collect could confirm one of our 30 theories, or it could shatter them all, revealing a truth about the universe's missing energy that we have not yet dared to dream. From the unwavering push of a cosmological constant to the violent possibility of a phantom-driven Big Rip, from the holographic projection of reality to the subtle leak of gravity into other dimensions, our journey across 30 theories reveals one undeniable truth. We are surrounded by a profound and magnificent mystery. The universe is 95% unknown, a canvas where our most brilliant ideas are but faint sketches. Some theories, like dark energy and cold dark matter, form the sturdy pillars of our standard model, yet they are haunted by gaps in our understanding. Others, from emergent gravity to the cosmic chameleon of the symmetron, dare to rewrite the very laws of physics. We have explored universes trapped in an endless cycle of birth and collision, and we have considered the humbling possibility that our entire existence is a rare bubble in an infinite multiverse. Each idea, whether grounded in quantum fields or cosmic information, represents a courageous attempt to answer the same fundamental question. What is the true nature of the cosmos we call home? This is not a puzzle that will be solved by a single experiment, but a grand detective story that will unfold over generations, driven by the next wave of telescopes and the bold minds that interpret their data. We want to hear which of these possibilities resonates most with you. Does your gut side with the elegant simplicity of a cosmological constant, or does the dynamic nature of Quintessence feel more compelling? Perhaps you are drawn to the radical idea of emergent gravity or the cosmic interconnectedness of quantum entanglement. Share your favorite theory in the comments below and tell us why it captures your imagination. If you enjoyed this deep dive into the universe's greatest secret, be sure to subscribe. Our channel is dedicated to exploring the edges of knowledge, from the strange physics of black holes to the search for life beyond Earth. The cosmos is full of mysteries waiting to be uncovered, and we are just getting started.